So thank you everyone for coming to our Innovative Discovery Series seminar. This is the last seminar of the year. Oh, it's not? Oh.
Penultimate.
Oh, sorry, we have another one in early December, sorry. But before introducing Dr. Sarwate, I will go through some housekeeping remarks. Make sure you sign in. Please RSVP so that we can better prepare for the next session. Sarah always sends reminders. Online participants, please keep mics muted unless asking a question and keep video turned off. Use the chat feature in BlueJeans if you have any technical questions. The next week seminar is Applying Network Theory to Medicine it's December 4th. It's not next week. Sorry. Finish out the calendar year, and then the following one will return January 8th with Applied Genomics, next generation sequencing in the clinical field. All the previous presentations are available on our website, DE-CTR.org. So we are delighted here today to have Dr. Sarwate with us. Dr. Anand Sarwate is currently Assistant Professor in the Department of Electrical and Computing Engineering at Rutgers in New Jersey. He obtained his PhD from the University of California, Berkeley, and his Bachelor of Science from the MIT. Prior to working at Rutgers, he was faculty at the Toyota Technological Institute at Chicago, and is PI or co-PI on a really large number of NSF or NIH grants, and has also a very long list of publications. So we are delighted to have you giving us a talk, and can't wait to learn more about differential privacy and all privacy issues.
Great. Thank you for inviting me. I have to say, when I found out this was a continuing medical education series, I was A, terrified because I'm not a physician in any way, but B, I could make my mother very proud because she is a pathologist. And so she was like, oh, wow, you really made it. And I was like, okay. So today I'm actually going to talk only a little bit about differential privacy because I didn't really know if the crowd was going to be mostly, I thought the crowd would mostly not be biostatisticians, although I see there are a lot of biostatisticians here. So if you want to have some more, things with equations, there are almost no equations in this talk. I can go ahead and do it on the board, so feel free to ask questions. I'm happy to do that. So my background is in electrical engineering, in particular in sort of the math end of electrical engineering, something called information theory. And so I work quite a bit in statistics and computer science and engineering, mostly on designing algorithms or how to use computers to do statistics more efficiently. And optimization. But in the applications that I'm interested in are related to how to learn from data which is private. And so I've been doing this for the last few years, and I kind of want to talk a bit about the privacy landscape and what we are doing, or so what the sort of current trends are in the computer science literature about how to think about privacy. And so some of this is a little bit sort of policy philosophy, and some of it is a sort of description of some techniques. So I kind of hope at the end you get a sense of what the landscape is. And if you have any questions, I've sort of omitted some references on the slides. If you have any questions, I can definitely send you references. You can just shoot me an email. Okay, great. So really, the kind of systems that I'm interested in are systems in which you share data, because now that we have, and so what do we mean by data sharing? So I put up slides like this. You have like an EMR, and you have some scanning machines, and a sequencer, and then this is the center that I used to work at when I was a postdoc in San Diego. But basically, it all boils down to this sort of formula. We have a lot better computing systems, a lot better, cheaper storage, and more efficient networks and databases. And we're better at measuring things. We can measure things faster. We can measure more data at once. So we kind of have this explosion of available data and the ability to do computation on it. And so this leads to a lot of new interesting challenges. Well, the difficulty is, of course, the more data you get about an individual, the sort of more individually identifying it is. But actually, what I hope I'll sort of make clear is that the amount of information that you need to individually identify somebody is actually quite small. So what can we do with this kind of data, I guess, from the context of healthcare and medical research is, there's stuff like just, quality assurance type of thing. So you can do more automated QA stuff in the hospital. You can design decision support systems. When I was a postdoc, I worked with the medical informatics group at UC San Diego, which used to be a decision support group at Brigham and Women's. So they did a lot of work in decision support. You might be able to build better detectors as part of a decision support system. The big thing that was the push when I started working on this in this area was trying to allow clinical data to be secondarily used for research purposes. So how would you design systems that protect patient privacy in that setting? And then more recently, I've gotten interested in collaborative research centers and things like research consortia studying a particular disease, where you have different researchers who have data sets and they'd like to somehow collaborate, but you can't email the data sets between people because subjects haven't allowed that to happen. So in particular, since you mentioned this NIH award, I'm working on this project called Coinstack, which is a neuroinformatics suite. It's built on top of an existing neuroinformatics suite at MRN, which is the Mind Research Network in Albuquerque, New Mexico. So COINS, the existing system, basically does subject registration and tracking and holding of the data. So it really tries to unify the collection of data in these kind of experiments. In particular, they have quite a bit of data. They have 572 registered studies that they hold, with almost 500,000 clinical assessments and 40,000 MRI scans, which is quite a lot of data. And so the potential, the question is what potentially could you do with data of this type? So the Coinstack system that we're working on, which is just the project just started, is an extension that's going to hopefully allow researchers who kind of have an agreement to collaborate to be able to run automated statistical analyses on their data without actually having to pull the data in one place. And there are a lot of similar efforts in other areas. There's a system called Data Shield and a system called VIPAR, which have been proposed, and we're actually talking to the people who work on those systems to see if we can develop a kind of unified framework for thinking about these kind of problems. So just an example of why such a system would be useful, we did a little proof of concept experiment. So we had a bunch of data and we artificially split it into multiple sites. So what did we have? So we had data from several different institutions and studies which had looked at schizophrenia. They'd studied different aspects of schizophrenia. But in each of these studies, they had collected a structural MRI of the subjects. And so overall, we had about 389 patients, about split half between having schizophrenia and half controls. And so the question we wanted to answer is, okay, so each of the individual studies had, maybe tens of patients or tens of subjects, right? And so you couldn't really, the kinds of analyses you can do on tens of subjects with MRI on the MRI images is somewhat limited. So what we wanted to do is say, could we build a classification algorithm that would learn how to classify new subjects, new subjects actually, who had schizophrenia from the controls. So, can we just sort of look at the image and say, okay, so I'm relatively confident that this person actually has schizophrenia just based on their MRI. We did a little bit of cheating because we had to sort of figure out a good way of representing the images, and each one of these MRIs was about a 60,000 voxel image. And if you're familiar with MRI, they're not pixels, they're voxels because they're 3D volume segments, so they call them voxels. And so we had to reduce it into sort of 50-dimensional representation. So some of the benefit we got here was a result of having what you would say in statistics maybe is having good features, right? So what did we get? So this is the kind of in a nutshell, we split the data into 10 sites, officially. We did many random splits of the data. We asked each site to try and learn a classifier that could classify schizophrenics from healthy controls. And each site on its own managed to produce a classifier which had about 20% error. So about 80% of the time, or maybe actually a little bit less even, because these bars are actually above the 20% line. So being nice to them would get about 20% error. However, if each of them share only, in fact, what they would share is only the classification rule that they used. And that rule was learned under what's called differential privacy, which we'll talk about later. So it was sort of a privacy-preserving statistical analysis. Shared that to some central aggregator. That central aggregator could merge those 10 individual rules into one single rule, which had about a 5% classification error rate, which is quite encouraging. It suggests that if you can incentivize these 10 different studies, the people who run these 10 different studies, to share access to their data, and in fact only share a very limited view of some local analysis of their data, we can take that and somehow merge it together and get a much better statistical result. So that's the kind of hope. All right. So the thing about when you talk about data sharing, and people often mean very different things, and in fact matters who's sharing to whom. And so if you want to taxonomize it a little bit, you can think about you could have institutions sharing data with each other. So Christiana Care might have an agreement with another institution to share access to data or share data. You might have an institution providing access to individual researchers at that institution. This is the kind of system I worked on at UCSD, which I'll talk about a little bit later. So, for example, you might have researchers trying to access the patient database to do the secondary use of clinical data. Or you might have an institution which just has to publish a public data set, right? And that's like a third problem. And so oftentimes we think about this. We think about data publishing. How do I publish data anonymously or safely to the public? But these other structures are, I think, kind of more interesting and are going to be more relevant in the future. So just to go a little bit into each of these structures, so institutions often do want to share data with each other. So you might have, in the case of different institutions with the same patient population, so there's some issue with, you might have outsourced your MRI to another institution, so you have to then link patient records and stuff like that. That's itself a kind of interesting and difficult problem. But if you think about the context of the schizophrenia study that I purport, putative schizophrenia study, if you didn't have an automated data sharing system, you would have to get the lawyers at every institution to talk to the lawyers at every other institution and execute these data use agreements. And we were writing our paper. One of the reviewers said, we wrote in the paper, yeah, it might take a month or two. And then one of the reviewers said, actually, it took more than a year for me, and I gave up. I just decided not to do this study because the lawyers were just taking too long. So in order to implement a kind of automated institution-to-institution data sharing, we need better database software and kind of better secure communication systems. But that stuff is available. It's just a matter of implementing it and kind of putting the technology together. This institution-to-individual sharing, so this IDASH Center is a National Center for Biomedical Computing, one of those big NIH centers. It's at UC San Diego, and it's focused on data sharing and anonymization. So the challenge was to try and figure out how to do secondary use of clinical data for research purposes. So the person accessing the data is somehow vetted. So there's some additional security guarantee about the individuals who are going to be accessing this data. And the idea there would be maybe you can build a system which allows people to do sort of pre-study exploratory research in a private and safe way. And then afterwards, if they figure out that there's something interesting there, then they can go back to the IRB and ask for the actual data, and then they'll get the actual data, right? That would be so the question is, can you allow exploratory analysis in a safe way without violating the privacy of the individuals in the system? So again, it stopped me if I see now there's some confusion. So in the faces. So stop me if you have any questions. Otherwise, I'll keep going. So the benefit here is, of course, that users log in, so you can track what they're doing, and so this gives you an additional sort of security benefit that might help you also get an additional privacy benefit. Then there's institution sharing to the public, and the biggest example of this is, of course, like the Census Bureau. The census has to publish data about the census to the public. And so government agencies have a lot of are sort of legally mandated to do this. When I was in Chicago at the Toyota Technological Institute, I talked to people at the National Opinion Research Center, NORC, which warehouses a lot of government data. And a big challenge that they had is that I guess there was a court ruling or something came down the pipe which said that they had to somehow give public access to all the Medicare billing data. And they were really trying to figure out how to do that without essentially individually identifying all Medicare patients and what was that they were being treated for. So they were trying to figure out maybe we can make a system like the previous one where you could kind of ask questions, or maybe they could publish small micro tables of it, and how are they going to do that? And it seemed to be very stressful. So I don't know if they've managed to succeeded in this, but it actually seems somewhat impossible from my perspective to do that privately. There's also a lot of open data movements, right? So there's like a site called, since I work a little bit on MRI, there's OpenFMRI, which is sort of people, there's like a public use data sets of functional MRI data. And that's, that's I guess possible if people agree to let their data be put out there in the public. So there's also, I guess there's a couple of these patient sharing websites as well. But then, of course, the challenge here is that there's no tracking of how people use this data. They can try and merge it with other data to re-identify individuals. So this is actually a very hard problem, I think, to solve in a principled way. So another important aspect of modern data sharing, of course, is that the data sharing itself is automated. So data is often collected without your knowledge and shared without your knowledge and then linked without your knowledge. So I'm sure that, I guess this is where I ask the audience, do you have any good examples of things where this has happened to you or maybe to people that you know or that you've seen in the news? Something like this, not clinical related or not medical related. No? Really? I guess.
We're more likely thinking something without somebody's knowledge.
Well, I don't know. I mean, it depends on if you ever looked at any of the side banner ads that you've seen while you're browsing, right? So who's sharing data to whom? Who's Google sharing data to that they know that while you're on the New York Times that you'll be interested? There's a banner ad that says that you should perhaps be interested in this, right? There's that famous case about Target. I don't know if people heard about this Target case where this young woman was, I guess, pregnant without her knowledge, or with her knowledge, but not without her parents' knowledge, because Target, from her buying patterns, inferred that she had similar buying patterns to people who were pregnant. So she started sending her, coupons for diapers and so on, and her parents found out, and it was a big deal. And so this is the kind of thing that happens in the commercial space, right? So so the question is, how do we do safer data sharing? I mean, we or you and as sort of professionals with kind of actual more sensitive data probably want to not be like Target, right? Okay. The questions for this talk is, what do we mean by privacy? What exactly is at risk? How do we think about the question of defining privacy? And what are the ways in which we might try to protect privacy while sharing data? And importantly, I get this a lot maybe because I'm sort of more in a technical computer sciencey type field. People say, oh yeah, privacy and security, or security and privacy, or privacy is a type of security. And they're kind of different. They ask different questions. And I guess then I will talk a little bit about methods that people typically use to protect data in these data sharing systems, and maybe some of the trade-offs in choosing one or the other of these. So since this is a continuing medical education talk, I had to put some education objectives. I guess this is a good teaching practice too, as I'm learning, as I start my teaching career. So these are the educational outcomes. So I hope that after the end of this talk, you'll be able to understand how these privacy challenges arise and identify some key differences between the different approaches in preserving privacy, and to understand some of the basic definitions, maybe not at a technical mathematical level, although I'm happy to do that on the board, but just understand what the differences are between these privacy frameworks and definitions, and then understand also how each of these frameworks is limited. No, there's no perfect solution. Everything is limited in some way. All right, and here's an outline for the rest of the talk. I don't need to go through this. Right. All right. So what is privacy, right? And so there's this great quote from 1975. It's an old law paper, or philosophy paper, I guess, which I really like because when you talk to people, I say I work on privacy, and they think, oh, Edward Snowden. And I said, no, I do not work on Edward Snowden-related privacy, right? But so we have to sort of define what we mean by privacy in the context of this data sharing systems. Like, what does it mean to keep something private? And I guess one way to think about it is privacy is like confidentiality. But there's kind of a difference between a don't ask and a don't tell in there. So, so just to get the security question out of the way, privacy is not security, right? Because when you talk about security, we're concerned about things like, can our database be hacked and downloaded? It happened to me when I was a grad student, or after I was a grad student at Berkeley. I got this email saying that somehow all of the Berkeley student medical records were hacked, or many of them were hacked and stolen, and including mine. So I guess they could know that I was having problems sleeping when I was in graduate school. But I mean, so I didn't feel so particularly violated by this, but it's bad, right? Obviously. Is the data encrypted when it's stored on the server? So this is also a very important question. And I mean, it should be, but it makes it slow because then every time you access the database, you have to decrypt, and that costs time. So I don't know if any of you have had problems. I don't know if you do use Epic here. No, you use something other than Epic. It's amazing. Everybody seems to use Epic. But anyway, if you've ever had problems with your EMR system, like being slow, you can imagine making it even slower by doing more encryption. And then you can see how frustrated you are at your job. And then the questions of user authentication. Is the user have the right credentials to access this thing? These are security type questions, and different from, I think, privacy type questions. The things that we worry about with respect to privacy are at least things like, will my boss learn that I have clinical depression? Because in the US, at least as far as I understand, it's perfectly legal to discriminate on the basis of mental health conditions. So this is why I'm interested in these schizophrenia studies and working on these neuroimaging and mental health studies, because these people who are subjects in these studies are basically, it's sort of legally okay to discriminate against them. Will Amazon know, based on my Google searches, that I'm My Little Pony fan? Maybe I don't want Amazon to know that and start sending me steep discounts for, Friendship is Magic T-shirts, right? Okay, so more seriously, what does when a patient comes in, what are the patient or subject fears in this sort of data sharing scenario? So patients obviously share a lot of very sensitive information, their medical history, their family's medical history, also health adjacent personal information, stuff like I'm going through a divorce right now, which impacts their health. And so we have these informed consent forms, which can authorize sharing, and you can say, but they're many pages long and people don't read them and they just kind of sign things or don't sign things. But it can really benefit clinical research and quality of care, and also tracking what services people are using. So it'd be great if they could, and oftentimes, and people in general surveys, the sort of surveys of user sentiment or like patient sentiment, is that people are actually quite willing to help make better healthcare by sharing their data, but they have some concerns about the way the data is used. And so the question is, how are you, how are you going to share this information? They're going to maybe use that information to refer them to some other physician, or you're going to get a prescription written, so that information is going to go to, say, a pharmacy, and or some information will go to the public statistics bureau, and you might use it for education. I know somebody who went to the dermatologist and they said, oh, your tinea is a great contrast. I would like to take a picture for, so I can present this when so they're going to use it for education, right? So what are people afraid of? They're afraid of maybe their employers finding out about their medical history, right? They're afraid about companies finding about their medical history, the companies that they haven't authorized. And I guess maybe this is a little less important now, but they're still afraid, even though you can't deny coverage, right, under the Affordable Care Act, they're still afraid of insurance companies finding out about various things. And I think these fears are legitimate because this is a diagram from California of how prescribing data is shared. So Calvin, the patient, goes to their provider, and data goes to the pharmacy, the hospital, and long-term care system, these vendors, various vendor systems. And notice these red lines are where the data has actually been kind of explicitly de-identified. In other lines, the data is not de-identified or it's not known what's happening. You have these different layers, and you can analyze, you can look at sort of how data is being shared, and I think that patients actually are kind of unaware that the pharmaceutical company is actually learning quite a bit about them based on the fact that they're being prescribed something, right? If you look at just lab results, you can get a similar flow chart for lab results. I think that if I get a lipid panel done, I'd be kind of, my pre-employment screening vendor is probably, I really don't want my lipid panel to be going to my pre-employment screening vendor, right? So, and then you can do this also for like, you call an ambulance, right? So the emergency health response, right? Stuff like that goes to the CDC. It goes to a lot of public health entities, right? In addition to going to the hospital and various other people, right? So these fears, I think, of how we share data are somewhat legitimate in the sense that, once that system, if that system gets linked to a commercial system, which it will for the, be bad. So people are afraid that out of the results of some data being published, that some evil genius is going to, and the thing is, it doesn't have to be an evil genius anymore. In fact, he's not a genius, right, in the movie. He's kind of an idiot. So we'll figure out who you are, right? So how do we? You might feel safer if the information is somehow shared more carefully. You can think of sort of 3 A's about how to share more carefully. Maybe you want it to be anonymous because you want, if you don't need the identifiers for you, obviously the CVS needs to know who you are in order so that you can pick up your prescription. So a little bit there, but it has to be. Maybe you'd feel even more safe if it was aggregated. So not just de-identified, but aggregated. So you just know how many people in this zip code are taking your drug. It'd be okay if the pharma company learned that. And maybe you'd be happy if things were only approximate. So instead of saying, oh, there are 355 people taking Lipitor in this zip code, which is probably low, right? You would say, oh, there's between 300 and 400. So you might be happier if that. And so the question is, can we get away with just doing that, right? So here's HIPAA. I'm sure everybody's familiar with HIPAA in this room. So this is the HIPAA expert determination rule, right? So HIPAA has 2 ways of releasing data. One is expert determination. It says a person with approximate knowledge and experience with generally accepted statistical and scientific principles and methods. I'm bolding the things which seem a bit problematic to me. What is the things that aren't defined, right? What is appropriate knowledge? What is generally accepted? What is defining that the risk is very small? What does it mean to say the risk is very small? What is reasonably available information? The reasonably available information at the time that HIPAA was written is very different than the reasonably available information now that you can just get from web searches. Do you really know who the anticipated recipient is? Do you have any concerns about maybe further sharing that happens? What does it mean to identify an individual? And what does it mean to document the methods? Right? How much about the methods are you revealing? The Census Bureau doesn't actually reveal a lot of the specific methods that they use on individual data sets because then their fear that somebody could undo that, right? So if you use a method like that and you don't reveal it, then you're sort of not following this rule, right? So what's the problem with expert determination? Is it has all these undefined terms such as appropriate knowledge and all of these, right? And so in some sense, I would feel uncomfortable being the expert that determines whether or not some certain data can be released, right? Because I don't think I'd be able to answer these kind of questions in a reasonable way. I wouldn't have enough. It's not possible to get the knowledge to know the answer to all of these questions. So here's a cautionary tale. I don't know how many people are familiar with this LaTanya Sweeney identification story. Nobody? Great. No, it's wonderful because when I have to give a talk to privacy researchers, they're really sick of this story. Okay, so this is the institution to public data sharing scenario. So this is from 1997. So it used to be, maybe it still is in some places, that hospitals are required to publish discharge records publicly. Discharge record would contain information about what was being used at that, or you could get it from a public records request. And at least at that time, and so it would contain information about, a patient came in on this day, was diagnosed with this, and this was the procedure that was done, and then some demographic information about the patient that would be useful for, say, provisioning resources, healthcare resources in the future, such as their zip code, their birth date, and their sex, right? So LaTanya Sweeney, so this is useful for tracking healthcare usage in the system and this more efficient provisioning, right? And we want to track and detect trends. So this seemed like a good idea in 1997 and earlier. So it seemed reasonable because the names were removed. You don't have any names or addresses or anything like that, right? You have zip code, but that's a pretty big area, right? And this was in Mount Auburn Hospital in Cambridge, Massachusetts, if you've ever been there. So what LaTanya Sweeney did is she went down and bought for $20 the voter registration list for the city of Cambridge, which contained all of these identifiers, including name, address, the party when you last voted, and the date you last voted, which you can buy for $20. And then contained also zip code, birth date, and sex, right? So he linked these two tables and found that, in fact, there were several unique zip code, birth date, sex combinations in the data set, and discovered that the governor of Massachusetts, William Weld at the time, had been to Mount Auburn Hospital in this state, was diagnosed with this condition, and this procedure was done on them, right? So this was bad. LaTanya Sweeney, she's at Harvard now. She's done several studies of this type, some of which have been actually sealed by court, banned from publication by court order. She did an attack on the National Cancer Registry that had a similar kind of effect. And there's a guy, Brad Malin at Vanderbilt, who basically has a paper saying, what's the cost of doing this attack across the country, because voter registration lists have different costs in different places. And the answer is, pretty cheap. So pretty cheap to do this. So you shouldn't release this sort of data publicly, right? Okay, so maybe de-identifying the data in this way, where you remove things that you think of as being individually identifying, is bad, because in combination with other things that could be individually identifying. So here's the other part of HIPAA. This is the HIPAA safe harbor clause, which gives a bit more about what you should remove in order to publish a data set. So there are all of these things, names, 3-digit zips are okay. So that maybe gets rid of the 5-digit zip code problem. So LaTanya Sweeney has also shown that, or it has an estimate basically that about 60% or something, more than half of the U.S. is identifiable from zip code, birth date, and sex alone, because birth date is pretty specific. So so it doesn't take much to identify you. I guess I said that I was going to convince you of that in the beginning of the talk. So that is the point. Phone numbers, all of these things look like, yeah, these are kind of individual identifiers, right? Don't give your social security number, but even your IP address. So this seems pretty good, right? I basically removed everything that seems to be individually identifying about a person, except for the problem with this rule is that the last thing is any other unique identifying number, characteristic, or code. So I don't know how to do this, and we can see an example where surprising things may also be individually identifying, right? And that's this Netflix. So who has heard of Netflix? Okay, good. I assume that laughing means yes, you've heard of Netflix, but who's heard of the Netflix Prize? Okay, so some people. So most people haven't. The Netflix Prize was a competition that Netflix ran. What they did is they wanted to get a better movie recommendation system. So they published a data set, which just was a list of just like person 1 rented these movies and gave them this many stars. And person 2 rented these movies and gave them this many stars. So you can think of it as like a big table, most of which is blank, like a big spreadsheet. Most of the cells are blank, except for a few numbers here, like movies and people, right? So they released this publicly and said, we'll give you $1 million if you can, for the best algorithm for coming up with better movie recommendations. And this seemed like a great idea. Lots of people tried it out. A team eventually won. And then they were going to, had a phase 2 Netflix competition that they're going to do because they had been so successful. They really did improve their movie recommendations. So these records contain a random identifier, so just like person 1, person 2, and a list of movies and the ratings. And so what some researchers, Arvind Narayanan, who's at Princeton now, and Vitaly Shmatikov, who's advisor at UT Austin, is now at Cornell Tech, found the same pattern of movies had been rated by somebody who had an IMDb profile, linked those two people, then did IMDb, is the Internet Movie Database. So if you ever wanted to waste a lot of time, you can go to imdb.com, and then you can find out who was in which movie. You can figure out. You can go to Kevin Bacon's page and see all the movies. And people use actually IMDb to do the 3 degrees of Kevin Bacon thing. So it's a great resource. So they re-identified a Netflix customer which violated the privacy agreement that Netflix had made with their customers, that they wouldn't be individually identifiable, right? And okay, so you might say, oh, that's because this person had a profile on IMDb, but still Netflix tried to make a promise, right? And Netflix was unable to actually make that promise or keep that promise. So both of these attacks are types of linkage attacks. You have an anonymized data table that somebody best effort tried to make anonymous by removing as many identifiers as they could. Then there's other public data, right? Which is out there, which you can buy for cheap, or you can just search for on the web, and then you can link these two, and then you can re-identify somebody, right? So you realize that this little pawn here is actually the guy in the blue hat, right? And you can do this. You can play this game with a lot of different anonymization mechanisms that we typically use, right? So what we want to do is then focus on what is the agreement that Netflix is trying to make to their customers, what is the agreement that the hospital wants to make to the patient in these kind of informed consent procedures, right? The difficulty, this is my privacy is hard to define, the blind man and the elephant picture. So one thing is that the published outputs, whatever you publish about the patients, can allow some kind of reinference. It might not be successfully, you might not be able to successfully infer somebody's identity, but people can try, right? And so we can see here that sometimes, this identification may be successful. Not everybody's records could be linked, but many could. And the other thing is that the data itself is inherently identifying, and I think that's what points out to the Netflix example. The pattern of movies that you have watched and how you like those movies is pretty much unique to you. So you can feel like you're good. I'm a unique snowflake, but that's bad for privacy purposes because it means that nobody has the same taste as you, and therefore just your taste in movies is identifying. We used to identify you. As long as there's another data set there which does have your name in it, people can find, right? And so the third point is that I think risk should be guaranteed to individuals. I think what you're trying to make is an individual guarantee to an individual patient. You're not trying to say you're going to be protected because you are in a group of a bunch of other people, because you could still do this linkage attack and re-identify a single person, pick up a single person out of that. There's another a study which I think is quite interesting. It's by here where they did an attack on the genome-wide association study, where they could show that if you had a sample from somebody, you could figure out if they were part of the genome-wide association study, just by looking at their SNPs, their single nucleotide polymorphisms. So, things are very uniquely. Obviously your genome is very uniquely identifying to you, but you can also be picked out of a crowd, even though the GWAS only publishes aggregate statistics. So privacy is lost every time we handle this data, right? And that's the real issue. And so we want to protect privacy while processing the data. That's the goal. But of course, there's always a trade-off, right? And we want to be able to trade off how private we make the data, or how we can control the privacy risk with how useful the data is. There's a paper which I was just reading this morning, which talks about Census Bureau methods, which talks about how certain methods used by the census might render certain analyses that you could make on, say, the American Community Survey problematic. It can change the results because of the processing they do for privacy preservation. So you want to make sure you can kind of understand the trade-offs that are there, and you also want to this quantifiable privacy risk would allow maybe individual patients to make, or individual subjects to kind of make a determination about how much protection they want, and they can make more informed decisions. Okay. So just to recap, the key challenges in these data sharing scenarios, that privacy is a little bit like confidentiality, because individuals don't want to be identified as participants in a study or data set. Similarly, a patient doesn't want you talking about them to somebody else, right? But data that is sort of with good intentions anonymized can be often linked with auxiliary information to re-identify individuals, and that identification only becomes easier the more data we have available online, and the easier it is to have the more databases we have about people. And then balancing privacy and utility is very important. And I think this is the big challenge, both from my end, from the kind of methods, statistical methods, computational methods, and research end, but also trying to understand what are the constraints on the end of the person who's going to end up using the data. How can I translate that back into saying, well, I can guarantee you this much privacy if you need to have this much accuracy. So when we think about PHI, we should think about what the structure of sharing is, these three different modes of sharing. Who's doing the sharing to whom? Because the kind of solutions you're going to get are going to be different depending on which of those structures you have. You want to be able to quantify this risk of an individual being identified from what is being shared. So the process of creating the thing to be shared is what is going to violate privacy. Then you also have to understand, like we saw before, what are the different controls under how that information is further shared. So if you have, if you have have security guarantees and you'll have to log in and so on, you can track individuals and you have legal sanctions. That's a different scenario than if you're publishing a data set to the public and then you have no idea, and there's no holds barred at that point. All right. So I'm going to move on to trying to understand the differences between different privacy technologies. Right? What are the ways in which we can do anonymization, and what are the other ways in which we can think about privacy technologically? Right. So we have these three scenarios. So the major distinction between privacy models and definitions is one between what the security researchers or privacy researchers would call syntactic and semantic privacy. So if you've had a linguistics class, you have a sense of the difference between syntax and semantics, but maybe not if you haven't. So syntax is grammar, right? It's the structure of sentences and so on. So syntactic means we are trying to guarantee privacy in terms of the structure of the data. So the goal is to kind of remove these markers of uniqueness from the data. This is what you do when you remove. You decide not in safe harbor. You decide to remove individual identifiers, but there are other things you can do in these syntactic privacy models to kind of manipulate the data to make it harder to pick out individuals. The other difference is the other one is semantic. So semantic is in terms of the data itself. So the goal is kind of ensure privacy through this process. This sharing process has privacy by making it ambiguous if an individual is present. So that is what you want to do is you want to give individuals, and I'll come to this soon. You want to give them plausible deniability about whether they were in the study or not. For example, when you publish data from a study. So how do you do that, right? And so in some sense, in diagrams, the question is where does the privacy guarantee? The privacy is pink, P for privacy. Where is the privacy guarantee being made? And semantic privacy is being made in the arrow, right? It's being made in this process. Whereas in syntactic privacy, what you're doing is you're kind of releasing a data set which you've anonymized in some way, right? So this is sort of the expert determination and HIPAA and the safe harbor rule kind of fall into this camp often because they're thinking about the problem in this way. I want to argue that maybe it's a slightly better way is to think about it in terms of this way. And here, what you do is you're making a privacy guarantee on the arrow, so you might not release actual data. You might actually only give somebody access to the data, and then you protect things as they access the data. So what are syntactic methods? They follow this kind of safe harbor formula. So they'll do is they'll generalize values. So instead of reporting age, they'll report age ranges. Instead of reporting, if you have a taxonomy, instead of reporting, a specific sarcoma, they'll just say sarcoma, right? So they'll not go and so that if you have like a taxonomy of cancers, you'll sort of report higher level of generality, right? So this is this generalization process. The goal is to try to make sure that individuals fall into groups. This in the Census Bureau language or official statistics language is sometimes called the rule of K. You want K people to all have the same values, and then you won't be able to tell the difference between those K people, so it's okay. The problem is that these kind of syntactic methods are subject to re-identification attacks, much like, even though Sweeney proposed this K-anonymity rule for protecting privacy, they're subject to re-identification attacks because if you have suppose you have two institutions serving the same patient population, they both do this sort of generalization process, you can still link those two things together, unless they do it exactly in the same way, and there's there's a lot of tight control over how everybody's doing their anonymization. So what are the kind of syntactic methods out there? There's something called top coding. Top coding means you don't want to report, you sort of trim the ranges. So like if people are very old, you're just going to remove them from the database. There's suppression where he's like, oh, these people are outliers. These people are too identifiable. We'll remove them from the database, or we'll suppress values which. There's microaggregation where you do kind of sort of more merging of people into bins so that they become less identifiable. There are things like data shuffling and sampling where I only give you a subsample of the data, or I do some sort of more manipulation. There's a nice, that paper that I mentioned about problems in the Census Bureau, it's from last year, talk about these methods and sort of their effect on how useful the data is. But you can see that they have different properties, like do you actually preserve the actual values of the data that you're using? Some of them yes, some of them no. Some of them will manipulate the data to the point where certain things are not reported, so the type of the data is not the same. Some will remove records from the data set, so that is bad for sample size, but maybe good for privacy. But all of them are going to result in some loss in the utility of your statistical analysis. Doing a statistical analysis on the raw data is much better than doing a statistical analysis on this anonymized data, right? So I'm going to make a controversial statement now. This is the controversial statement of this talk. These are not safe. They may not be. They may be slightly more useful than what I'm going to talk about, or may lead to some. Even though there's some problem, there could be problems there as well. But they're not really safe because of this linkage attack problem. So I think the reason they're not safe is because they're all predicated on I'm going to now share this data set to you, which is great if you're, which is mandatory if you're the Census Bureau, but not mandatory if you're not the Census Bureau, right? You don't have to publish data. So instead of saying, oh, here's a data set and I'm going to publish it across this privacy barrier, and then maybe I have access to this data set in my local institution. Instead, what I want to do is, might want to do is have a system where if you're a researcher or another center, you can ask questions about my private data. I will answer questions about my private data. We can maybe even make an automated system where these questions are computations and they're automated. But I'm not going to release the data to you. And there are only certain questions I'm willing to answer. And then that will maybe allow you to control what's being leaked. Right? That's a different process. That's sharing. The difference between sharing anonymized data and sharing access to private data. That's a big conceptual shift, perhaps, in the way that we think about these problems. So that falls into these notions of semantic privacy definitions. So let's do a little warm up on semantic privacy now, like kind of on the individual level, right? So this is the surveying problem, which is classical. So for those with the public health background, maybe you know the answer to this. So suppose we want to learn the fraction of pot smokers in the population, right? Of course, maybe you think this guy is actually the pot smoker, given the way he looks. But okay, but we don't care about individual responses, only the aggregate. We only care about the fraction p. We don't care about whether you're a pot smoker or I'm a pot smoker, right? But the surveyor is not trusted. He doesn't look trustworthy. Look at him. So how can we get these responses? So anybody know the answer to this? What's the technique for trying to elicit accurate answers from people? Or maybe not accurate answers from people, but learning this fraction. You can make it honest, but this is actually, like I'm going door to door and I want to, in my neighborhood in Jersey City. Actually, in my apartment building, I definitely know there's at least one. So, okay. So the answer is randomized response, something called randomized response. Has anybody heard of randomized response? Oh, no, nobody's heard of randomized response. This is great. Okay. So in randomized response, what you do is the surveyor says, okay, you don't trust me. So here's a coin. It's a biased coin, or it's like a random number generator. And it's a little bit biased. So maybe it'll come up heads, 60% of the time and tails 40% of the time. And so you go and flip the coin in private. Don't tell me what the answer, how it came up. And if it comes up heads, tell me the truth. And if it comes up tails, lie. All right? So, and I asked, I talked about this to a bunch of freshmen, and at the end of the class, end of the lecture, the only thing they wanted to ask me is if I smoke pot. So I had to run this protocol. It was very embarrassing. Suppose we survey 10,000 people and do this thing, right? And let them lie 40% of the time, right? So this is the only equations in this talk. True fraction of people who have smoked is say 38%. I made that number up. I did not look that up, right? Okay, so 38% of people have smoked pot. And so what we expect is out of 10,000 people, if I multiply by 0.38, I'll get about 38. In the real population, you have about 3,800 smokers, and of those, 60% will not lie to me, and I'll get about 2,280, and those people will say yes. And what I expect is that, okay, so 1 minus p, which is the fraction of non-smokers, so this is the number of non-smokers, 6,200, 10,000 times 6.62. Of those, 40% of those are going to lie to me and tell me they do smoke pot. Right, and so this is 2,480 of them. So those are the total. So these are the total number of yeses. The number of people who say yes is the sum of these two numbers, which is 0.6 times np plus 0.4 times n times 1 minus p. And then this is just out, and then I know the number of people who said yes, and I just solve for p. Right, just do a little bit of algebra. And so the great thing about this protocol is that, okay, subject to sampling error. So all the statisticians are like, oh yeah, but what about binomial random variables and blah blah blah. Okay, subject to all the sampling error, as long as the fraction of people who are allowed to lie isn't half, and you have a large enough sample size, you will get a relatively accurate estimate of the true fraction of pot smokers, and everybody's allowed to lie to you, and everybody feels kind of okay about this protocol because they have plausible deniability about whether even if they said yes, right? Even if they're a true yes, right? So this is actually what differential privacy does. So maybe if some of you were at the workshop that I presented at before, there was a long talk about differential privacy with a lot of definitions. throw that out. Differential privacy, for the purposes of kind of understanding the broad scope of it, differential privacy is a way of letting people get randomized response like plausible deniability, but for more complicated things than just asking for the fraction of pot smokers in the population. You want to be able to compute more complicated functions, more complicated statistics, right? So what you're doing is you're preventing the, so just in a nutshell, is that, so you kind of posit a world in which, here's your true data, and here's a data set where this person, changed from not being a pot smoker to being a pot smoker. So there are two possible worlds, and from the perspective of the privacy for individual N, they have you look at the two possible states they have. You have an algorithm. This algorithm is differentially private, and what it does is it produces a kind of random outcome. And the point is that from looking at the output of this random outcome, you can't tell which of these two data sets was actually generating your result, or you have a hard time, right? And it just goes back to controlling, for the statisticians, it goes back to controlling a certain log likelihood ratio, and making the hypothesis testing problem hard. So what this lets you do is you can quantify the risk, which is often which is in the differential privacy literature is called epsilon. Use the letter epsilon for it. We control that risk, and that risk is essentially related to the coin. How biased is that coin flip in the randomized response protocol? The closer it is to a half, the more privacy, the more plausible deniability you have. Similarly, the smaller epsilon is the less epsilon is privacy risk, so the less risk you face. But the point is, the closer that coin goes to a half, the larger a sample size you'll need to get an accurate estimate of p. So similarly, as epsilon goes to 0, the more larger sample size you're going to need to get an accurate estimate of whatever more complicated function or statistic you want of your data. So differential privacy is very useful for this shared access to data model, because essentially what you're doing is, you're saying, here's a function I want to compute on your data, and the database system will say, the private database system will say, oh, okay, here's this function. Okay, I'm going to introduce some error or noise to make it differentially, some randomness to make it differentially private. Here is your approximate answer, right? So the data holder can say, okay, I paid epsilon for this transaction. I know now how much epsilon I've leaked to you, how much of a privacy risk I've leaked to you, and I will track that over time. And then maybe you go over budget, and I will say you're cut off. So it can be adapted to these institution to institution and institution to individual models. You can also try to formulate like the publishing a data set model for that, but it's trickier, and I'd say it's a little bit less prime time now. But the problem is, of course, that it's providing a randomized answer. So you're getting a lot less. You're not able to sit around and play with the data, right? So the answers to these queries are approximate and, or in this case, noisy. You've added error. And this is challenging for many applications. There was a paper which tried to look at can we make a differentially private dosing recommendation for a certain drug? And they were like, then they were plotting this privacy versus mortality curves, right? And like that, yes, you would not use it for that. You would not do this for that application, right? That's probably bad scenario. But privacy risk accrues over time. That's the other issue, right? But that's actually, we know that. The more I reveal about a data set, the more you can learn about that data set. So so over time, you're going to accrue this privacy risk. And finally, from maybe my perspective, there's been a lot of research in differential privacy, but many of the methods are not really ready for use in real systems, except for actually the US Census is using it for a kind of commute tracking application called On the Map, which you can look at. So that uses differentially private data. But that's the goal, actually, of this Coinstack system that I mentioned at the beginning that we're working on. We really want to see which of these differentially private methods can be brought, into use in a research system. Okay. Okay, so let's see how it can work but let's see how differential privacy might work in an institution to individual setting. So this is this cohort identification problem that I sort of mentioned at the beginning of the talk, when I was at UC San Diego, we were working on this. So suppose a researcher wants to find a cohort in an existing database of patients, right? And so they're going to make queries and they're going to get answers, right? And so typically what you might do, and maybe you can correct me, this is my understanding of this is how people told me that they do it, but maybe you do it differently. They're going to ask a sequence of queries to narrow down the cohort, right? To see if they can get a reasonable size cohort. So, you might start, okay, how many males are there between 30 and 40? And then you're like, a lot. And then you'll say, okay, how many of them have diabetes? Okay, maybe fewer. And like, okay, how about diabetes and hypertension? And then, you start getting smaller and smaller sample sizes. And then, so the existing systems that we have for this often provide kind of approximate answers. There's a system called I2B2, and a system called Stride. I think I2B2 is used at partners, and so they'll give sort of approximate answers of the counts of the individuals here, right? But they don't offer a sort of quantifiable privacy guarantee. And also, all they do is return counts. Like, you really would like to be able to ask slightly more interesting questions, like, if I do a regression, is there a line there, or is it just garbage, right? So this restrictions limit the number of times a query can be repeated. So the restrictions that are offered in like I2B2 is don't ask the same question 6 times so that you can average out the error that I've added in, so you get the exact number. Like, that's not okay. And you can see why the privacy risk happens here. Like, I could just go, okay, 30 to 41, and then add a bunch of things, and eventually figure out that there's one person who's 40 with all these conditions, one person who's 41 with all these conditions, and I know that this person is 41, so I know that's that person, right? So, you can see there's a problem there. So a very simple differentially private solution might be to do kind of what we do before, but only track the amount of times, track the kind of questions that are being asked, and sort of understand the sequence of questions and how much privacy is being leaked by each one. So we can choose epsilon to match the existing sort of noise that people get to face in these systems that they're happy enough to use for cohort identification. And so then we can see what kind of epsilon that we get there. But now we can do lots of other things because we know more. We're actually understanding with the privacy utility trade-off, the type of error that's being introduced, and the amount of privacy that we're introducing. We can start doing things like tuning for over and underestimates. Maybe you want to have you're okay with underestimates, but not okay with overestimates because you want to have enough statistical power. Various other things you can do. You can start letting people ask more complicated questions. Do the regression, for example. What does the regression look like? This quantifiable privacy allows you to you can give somebody a privacy budget in the potential future system, which says, okay, for your pre-exploratory analysis, you have this much budget to ask questions to the database system. Ask the questions how you want. And then if you find something, then you can go to the IRB then and get the actual data, right? It also allows for different trust levels for role-based access. So different people, you might have an assistant, you might have a graduate student, and then you might have who's allowed less access than, say, a postdoc or something like that, or an actual researcher, scientist at the institution, right? So this is a privacy currency. This is what differential privacy lets you have, a kind of privacy currency to talk about the risk-reward or risk-utility trade-off, right? Which is kind of absent in the anonymization framework. So looking forward, I guess, so this system is being integrated, I think, into the UCSD clinical data warehouse that they have there. And the goal, of course, is to incorporate other statistical tasks to let more rich analyses of these kind of make those possible. And of course, I think there's lots of really interesting questions here in terms of research and also in terms of data visualization. As a researcher who might be interested in using this kind of system, what kind of visualizations, what kind of ways in which you'd like to access the data would be useful, right? And that will help. That kind of feedback helps guide what methods people work on, like me, who don't actually do this type of work, right? So what kind of queries would you like to run? That's a question. Okay, so just as a recap, there are several different concepts I think to think about here. Is privacy versus security. They're very different from each other. And security is concerned about encryption and stuff like that, and privacy is concerned about this data sharing and leakage type problem. There's these differences between syntactic and semantic privacy. Clearly, I fall on the semantic privacy on the bandwagon, but I don't want to. Syntactic privacy methods are very useful and very commonly used. And there's a big difference, I think, between sharing data versus sharing access to data. I think that's the biggest thing. That's the biggest shift that's going to happen. And guaranteeing privacy, even if you do syntactic or semantic, you're always going to lose some utility, right? So the kind of the trade-offs are syntactic methods offer you more control in how you can control the age ranges that you pick and stuff like that. You have more control, whereas differential privacy, you're just kind of adding noise. You're introducing randomness, which creates a kind of unstructured uncertainty, whereas it has a more structured uncertainty. But these methods might not be safe, and these methods, of course, might not be as useful. So in all applications. So this is the kind of trade-offs that I mentioned before and limitations. So just, I know I'm maybe a little bit over time, so I'll just go through this. So these were the goals for the talk. I hope you remember them when you have to take your quiz afterwards. So I think what I want to close for is I think there's real need for standards in this space that we don't have. We have HIPAA. HIPAA is a law. HIPAA is written by law people. people. So they're written by, and so all these things are not really well defined. Like we don't have like a technical understanding of what's going on. So, we have these legal definitions. And I think that, it might be possible. I have hopes, maybe because I used to work in wireless communications, that we could have 802.11 equivalent, sort of standard levels for how we do these data sharing systems. And then we can update those standards as privacy technologies improve and so on. And the final point I want to make is that privacy loss is really, kind of a Pandora's box. So once you sort of leak something and violate privacy, do something that's privacy insensitive, if you like, it's very hard to go back. You can't go and fix it. The data's out there. So just some concluding point is that I think calls for data sharing are really going to increase now that everything is in a database. And I think safety, reliability, and ethics are important. And I think ethics often gets dropped out of these conversations, although it's clearly more important and more relevant, more on your minds than maybe it is on the technologists' minds. I think we're going to see some more complex models, but hopefully simpler to use models for informed consent. So the question is, there's an unknown unknowns problem there. If you're going to be sharing somebody's data later on, how can they consent? What should they be consenting to? Especially if a new data sharing application comes up, new instance comes up, are you going to go back and ask them, or do you consent to this new type of sharing? How do we do that? How do we let people understand how their data, those complicated charts that I showed, how are we going to explain that to them? I think we're going to see some more careful monitoring and tracking of access, which my cousin was working in the UCLA hospital when Michael Jackson was brought in. He was terrible. It was terrible. Like the way in which people, could access records was not particularly, did not feel particularly safe to him. So I think there are a lot of tough calls, I think, between this balance between privacy and utility, and also and utility can be all sorts of things, statistical stuff, but it can also be just ease of use. You don't want quality of care to go down just because you're put in a lot of extra hurdles that make it hard to do. Okay, so thank you very much.
So that's wonderful and very revealing and very scary. So we're at the other end of the spectrum from you. We're data aggregators, complex data people, but babes in the woods when it comes to how to deal with establishing privacy, even though we want to.
Right.
So where do people like us begin? How do we go about this in a rational kind of way?
Well, I guess again, it's thinking a bit like an engineer, right? You want to kind of figure out. So the question is, you have some sort of internal desires to share something, and maybe you have some external requests for data, right? So you have to kind of figure out what is the nature of what's being asked. How much. So obviously, people would be very happy if you just kind of let them log in and ask whatever questions they want. But what do they really need for the task? I think that's the thing. Is I think being able to break down because we're very comfortable working on stuff on our own, when we have it. But then when we have the data here, but the question is, okay, but now if I push the database away from me, what is it that I actually need answered? And I think that's actually tricky. That's a computational problem. But I think identifying what the tasks are that you actually have when you actually interact with the data, what you're actually doing, I think is one place to start.
Yeah. Well, it's a good answer. I mean, I think part of the problem with that is that once you develop a database that's really interesting,
right,
everyone wants.
Right. No, I think it's it's like a mindfulness. It's like a mindfulness practice. As you should be mindful while using the data and kind of step back and say, well, what am I doing here? And then it's challenging. But this is this point that I made that
ethics aren't going to do. You actually have to you have to prevent the bad guys, right? What you really want to do is prevent the bad guys who are going to come and do something unethical.
Right. Well, the question is,
this room is incredibly ethical, but some bad guys.
Well, no, that's the thing. So if they're bad guys in your institution, then that's a different beast. That's why I said that the presence of having legal sanctions and so on is kind of an aid. If you talk to people who are kind of hardcore differential privacy people, they would say, oh, well, every time the threat model that they call the threat model in security is that everybody out there to whom you've shared anything. So all the researchers could collaborate, even though they're working on independent studies, they could be collaborating and sharing all the results, and then they could be trying very hard to re-identify individuals, right? But that is probably not the case. So yeah, well, no. So part of it I think is really better training about data, data use practice, right? So I think you have protocols for and safety standards for patient care, like you're doing a stick and getting blood. The phlebotomist has like a protocol that they have to follow. You should also have a protocol for accessing databases, right? I mean, it should be like that. That's what I mean by it's another part of standards, right? Is that it can't be just it's in the computer system, so I'll just around, cut and paste this thing into this search engine and search something and then come back. Google can look at the searches that come out, from a particular IP address, right? And they could figure out a lot about what your patients are doing, right?
And they probably do.
Or So I mean, I guess it's already hard in a hospital setting. I know with the things being siloed in certain machines, but in some sense, the military services have a kind of correct approach to this. Like, the laptops cannot be connected to each other, sort of thing.
I mean, I guess that's what we do also here. But I think, and you are probably aware of that, more and more, when we have NIH grants or NSF, there is a requirement for, and we need to put together a plan for sharing data.
Right.
So what do you do then?
Well, I think that's the benefit of this sort of this data shield. So there's two. Okay, so I guess. Right, so that's coming as a mandate from the top. And I think it's a very good point. I think that the coin system, the way that they have it there, is like sort of a start where maybe you get to put in some limitations about. You can't just publish the data. What you should publish is kind of an interface to the data set, and then the question is what kind of protections do you feel are necessary, or is the NIH okay with having on the access to that data set? And right now they think about it in terms of like embargoes, right? It's like, okay, you can embargo the data for a year, or whatever it is, 6 months, a year, something like that. And I had some rule where it's like you can embargo the data for a year and then you have to share it, but they don't actually say what they mean by sharing. So I think that's the point. That's where the
and also public data sets that are, for research like NHANES,
right.
It's a major data set that anybody can access. I mean, I think you need to have, some type of justification for accessing it, but I think it's very minimal.
Well, so in the response to this attack on the genome-wide association study, I think they did that with the genome-wide association study. I think they then said, okay, you can get the data if you send in a page, fill out a form and send in a page justification of why you need it, and then we'll send it to you. And then you have to sign a form saying you're not going to try to identify any individuals in the study, which of course just is actually bad from a privacy research perspective because you actually want to understand what's identifiable. So if you kind of say, I'm not going to try to do it, you preclude getting better. It's like saying I don't know. It's like our gun policy in the US. It's like saying, I don't want to introduce, I don't want to learn, I don't want to get the evidence about, I'm going to preclude getting evidence about potential privacy problems, preventing people from looking for privacy problems.
So how are these public data sets?
No. So that that's what I mean by this tricky balance. So people just somebody has made the decision that the breaking a few eggs or whatever you can learn about individuals from this public data set is worth having the public data set. And that's what I mean by tough calls, right? So I've met people who say, we should just make all this data public. Because they think that the benefits are so outweigh the costs that, that's their decision. So I think there are some data sets which, you might say it's more important to make this public than to not make it public. To see what that says about whatever consent forms that you have for people who agree to do the study.
How can you tell what kind of harm is possible with the data that you're publishing? I mean, when you're creating that data set,
right.
When Google collects information about my searches and Zulily knows I shop for shoes, that's really not bothering me. I mean,
right.
it's kind of a little spooky when all of a sudden the shoes I was looking at pop up on every website.
Right.
but it's not causing me any harm.
Right.
So how do you measure the harm?
Well, so that's
Potential harm?
actually still an open research question. I think that also it's very subjective, right? So your nonchalance about shoes, your information about your shoe tastes, may be quite violating.
Pregnancy test, they might do quite-
No, but even shoes. No, I'm saying even shoes, right? Somebody else might say, feel very violated by this. So this is like an individual subjective decision. Some people are quite happy to let their medical history be kind of public, right? There's this, not 23andMe, it's not 23andMe, what's the company? Patients Like Me or something like that? There's a data sharing portal where people essentially upload their entire record because they want to find other people like them, and then they have a discussion about it. And this guy who is the director of the center I was in at UCSD, not the informatics center, but other engineering center, he does this, and he's like a total evangelist about it. He thinks it's great, but he also seems like a pretty healthy guy and probably doesn't have like too many serious health conditions. So,
you can't tell what the potential.
You can't, and that's the whole point actually of these attacks that I described. You can't understand what people are going to do with the data if you publish data like that. Just publish and so the thing about differential privacy is what you can do is you can quantify this risk. In differential privacy, you can say, okay, here I published a version of my data which is differentially private. But if you have a small subject size, that data is not going to be very useful because you're going to have to add so much noise to guarantee privacy. And the other challenge is that, and in addition to the usefulness, is that so the benefit is that according to the definition, it doesn't matter what auxiliary information is out there. So there you have controlled actually the risk. But you may have also made the data useless. So
Yeah, might not have enough accuracy
right
to predict outcomes.
to predict outcomes. So what you have to leverage is like a large sample size. Like differential privacy makes sense when you have trying to do large sample size and you're trying to ask these kind of public, retrospective type studies on existing populations. But it's not great for data publishing. That's actually the point, I think. And there are, so your options are don't publish the data, publish an interface to the data somehow. That's a thing that one has to try and develop. And the other thing is, would be to, just say, okay, NIH says I have to do it. So then you have to revise your consent forms for the study.
Great, thank you very much.
We're really good at it.
So